have you ever just stopped for a second and thought about the invisible architecture all around us? We usually picture steel beams and concrete when we think of structure, right? But there is this entirely different kind of engineering happening right at the molecular level, and it literally dictates how we live, how we study, and how we communicate. So, welcome to this explainer. Today, we're going to take a nice calm dive and decode the truly fascinating world of plastics.
To keep things super clear, here's our roadmap for today. First, the architecture of plastics, then thermoplastics versus thermosetting. After that, we'll look at the everyday heroes, move on to heavy-duty engineering plastics, and finally wrap up with the biodegradable future.
Let's jump right into part 1, the architecture of plastics.
Take a second and just look around your room right now. Seriously, how many different types of plastics can you spot? You've got the casing of your laptop, the insulation on your phone charger, the frames of your glasses, maybe even the synthetic fibers in the chair you're sitting on. It's honestly almost impossible to count them all, and that perfectly illustrates why understanding this material is absolutely crucial to understanding our daily lives.
Okay, so here's the fundamental takeaway. Plastics are basically high molecular weight polymers, but what makes them so incredibly useful is a specific property called plasticity. All that really means is they can undergo a permanent deformation in their physical structure whenever we apply force or stress to them. By just tweaking heat, pressure, and adding specific catalysts, we can mold these amazing chemical chains into virtually any shape we want. Moving on to part 2, thermoplastics versus thermosetting.
Think of the entire polymer world as being split into two main camps. On one side, we have thermoplastics. These guys are made of linear or maybe slightly branched long chains, and they've got pretty weak secondary forces holding them together. So when you heat them up, they soften like wax, meaning you can melt and remold them over and over again. On the flip side, we've got thermosetting resins. These form highly cross-linked three-dimensional networks with really strong covalent bonds. When they get heated, they set permanently. It's kind of like cooking an egg, right? Once it's cooked, there's absolutely no way it's ever going back to a liquid state.
Let's get into part 3, the everyday heroes.
First up is a classic, PVC, or polyvinyl chloride. It is a crazy versatile thermoplastic polymer. It's actually produced by taking a monomer called vinyl chloride, which itself is made by reacting ethene with hydrogen chloride and heating it up. You do this in the presence of a catalyst, usually benzoyl peroxide, and boom, you get this long, repeating linear chain. What's genuinely amazing about PVC is just how customizable it is. In its pure, unplasticized form, rigid PVC is this chemically inert, super durable powder that gets turned into heavy-duty stuff like safety helmets and parts for your refrigerator. But if you just mix in some plasticizers, like dibutyl phthalate, uniformly with the resin, you can completely transform that exact same rigid plastic into the highly flexible material that makes up your raincoat, a handbag, or even your shower curtain. It's like molecular magic.
Let's look at another one of these everyday heroes, Teflon, otherwise known as polytetrafluoroethylene. If you check out its structure, you'll immediately notice those F atoms. That's fluorine. Teflon is prepped through the addition polymerization of tetrafluoroethylene, all done under high pressure.
Now, those highly electronegative fluorine atoms give Teflon some incredibly unique superpowers. Because of the super strong attractive forces within the molecule, it boasts extreme chemical resistance. We're talking resisting almost all chemicals, with the rare exceptions being hot alkali metals and hot fluorine. Plus, it has a surprisingly high melting point of 350 degrees Celsius.
And that explains exactly why Teflon is the ultimate undisputed choice for your non-stick frying pan. But its uses go way, way beyond cooking breakfast. Because it can withstand such intense heat and acts as a fantastic electrical insulator, engineers use it for heavy-duty industrial seals, gaskets, and for insulating wires and cables inside transformers. Moving right along to polycarbonates. Creating this specific thermoplastic usually involves a reaction between the sodium salts of bisphenol A and a rather intense chemical called phosgene. Now, interestingly enough, phosgene was originally used as a chemical weapon in World War I. But here, in this process, they combine totally harmlessly to produce an incredibly useful polycarbonate chain. Thanks to that structure, polycarbonates are exceptionally strong, stiff, tough, and completely transparent. They even keep their rigidity all the way up to 140 degrees Celsius. So they are highly reliable for everything from CDs, DVDs, and Blu-ray discs to projectile-resistant eye protection and even the sheer sheeting you see on greenhouses. All right, let's shift gears to part 4, heavy-duty engineering plastics.
Now we're going to explore a really historically significant thermosetting plastic, bakelite, which is also known as phenylformaldehyde resin. This is actually synthesized way back in 1909 by a scientist named Leo Baekeland. Bakelite requires a very specific multi-stage condensation reaction to achieve its famous permanent rigidity.
Let's break down how this builds step by step. In stage 1, phenol and formaldehyde react in the presence of either an acid or a base catalyst to form these simple structures called hydroxymethylphenols. Then, in stage 2, these undergo self-condensation to form a linear polymeric chain. This intermediate chain is what we call novolac.
But here is where the real structural shift happens. Upon further heating, usually mixed with a compound called hexamethylene tetrahydramine, those chains condense into a massive, permanent 3D cross-linked network. This dense web of chemical bonds is exactly why a thermosetting plastic like bakelite can never, ever be melted down again. Once it sets, it's literally set for life.
Because it easily withstands high heat, is ridiculously rigid, and possesses fantastic electrical insulation and abrasion resistance, bakelite is the perfect candidate for high-stress environments. We still use it for electrical switches, those classic heavy telephone parts, the adhesives in heavy grinding wheels, and even the bearings used in massive machinery like ship propeller shafts.
Finally, let's look ahead with Part 5, the biodegradable future.
So as we try to replace our dependency on fossil fuels, we can look to incredible new materials like polylactic acid, or PLA for short. This is an entirely biodegradable synthetic resin. Specifically, it's an aliphatic thermoplastic polyester, and honestly, it represents a massive leap forward in green chemistry. Here's the coolest part. Instead of starting with petrochemicals that we pumped out of the earth, we can literally harvest renewable resources, like everyday corn or sugarcane. We then use bacterial fermentation to turn the natural sugars from those crops into lactic acid. Finally, through condensation polymerization, we link all those lactic acid molecules together into a capable, heat-resistant plastic, PLA.
Because PLA has totally natural origins, its real-world applications are incredibly diverse. It's actually safe enough to be used inside the human body for biomedical stuff like dissolving sutures and drug delivery devices. We also use it for compost bags and eco-friendly food packaging. Oh, and if you've ever played around with a desktop 3D printer for a college project or hobby, PLA is almost certainly the standard filament you are melting down to build your models.
It really makes you wonder, if we can essentially brew capable, heat-resistant plastics from a literal field of corn today, how will biodegradable polymers completely reshape the factories of tomorrow? It opens up such a quiet, peaceful, and green path forward for the materials we rely on. So the next time you plug in your laptop charger or pick up a 3D printed model, maybe just take a brief moment to appreciate the invisible chemical architecture quietly holding it all together. Thanks so much for joining me for this explainer, and take care.